How many numbers would it take to fully describe your face? Consider the complexity. The exact curve of your lips, the spacing between your eyes, the subtle arch of each eyebrow, the texture of your skin at every millimeter. You'd need to catalog thousands upon thousands of measurements, perhaps millions, just to capture the physical architecture of a single human face with any precision. Now, think bigger. How many numbers would you need to describe the Earth? We'd have to account for every mountain range, every valley carved by ancient rivers, every grain of sand on every beach, the composition of the atmosphere at different altitudes, the temperature gradients in the oceans, the magnetic field variations across the globe. The number of parameters required would be astronomical, climbing into the billions and beyond. And that's just one planet, a relatively simple object in the grand cosmic scheme. What about a star like our Sun? Stars are roiling spheres of plasma, with fusion reactions occurring in their cores, convection currents churning through their interiors, magnetic fields threading through their atmospheres. To describe the Sun completely, we'd need to specify the position, velocity, and energy state of countless particles, the strength and direction of magnetic fields at every point, the chemical composition varying from core to surface. We're talking about numbers that dwarf human comprehension. Galaxies contain hundreds of billions of stars, each unique. Nebulae span light years, with swirling gases of varying density and composition. The complexity compounds endlessly. So what happens when we encounter the universe's most extreme objects, supermassive monsters that can weigh as much as billions of suns? Objects so dense they warp the very fabric of space and time itself. How many numbers would it take to describe a black hole? The answer will shake your understanding of reality itself. 3. Just 3 numbers. No more, no less. It doesn't matter if the black hole weighs as much as a mountain or as much as a billion stars. It doesn't matter whether it formed yesterday or 10 billion years ago. It doesn't matter if it sits at the center of our own galaxy or lurks in a distant corner of the observable universe. 3 numbers: mass, electric charge, and angular momentum are sufficient to completely and utterly define any black hole that exists or could ever exist. On the surface, this makes black holes seem almost trivial. Only 3 parameters? A child's toy has more complexity. And yet this simplicity masks one of the deepest mysteries in all of physics, a puzzle that has consumed the greatest minds of our era and continues to challenge our most fundamental assumptions about the nature of reality. Because here's the thing, there are infinite ways to create a black hole. You could form one by collecting dust and gas over billions of years, slowly accumulating mass until it reaches critical density and collapses under its own weight. You could witness the catastrophic death of a massive star, its core imploding in a Type II supernova, creating a black hole in an instant of violent transformation. You could watch 2 smaller black holes spiral together in a cosmic dance, merging to form a larger one in a collision that sends ripples through space-time itself. Or imagine something more elaborate. Picture gathering every book ever written, every photograph ever taken, every piece of data stored in every computer across 1,000 civilizations. Every poem, every equation, every mundane grocery list and profound philosophical treatise. Every memory of every conscious being that ever existed. Now, compress all of that information, all of that meaning, all of that history into a black hole. What happens to it all? According to physics, it all reduces to the same 3 numbers. The black hole that emerges doesn't care about what went into it. It has no memory of the encyclopedias, or the exploding stars, or the swirling dust clouds. All of that staggering complexity, all of that information, somehow vanishes behind the event horizon, leaving behind only mass, charge, and spin. This is the paradox that has haunted physicists for decades. How can an object formed from essentially infinite possibilities be described by just 3 parameters? Where does all the other information go? Has it been destroyed? Does it somehow survive in a form we don't yet understand? And most troubling of all, what does this tell us about the fundamental laws that govern our universe? The story of how we came to understand black holes begins not in the modern era of particle accelerators and supercomputers, but in a quiet English parsonage in the 1780 seconds. Life as a country clergyman in 18th century England offered certain advantages. The position came with a comfortable house, a reliable income, servants to handle domestic duties, and junior curates to manage the more tedious responsibilities like conducting services and visiting the sick. For those inclined toward laziness, It was a perfect sinecure, a life of genteel leisure with minimal demands. But for those with curious minds and intellectual ambition, it offered something far more valuable: time. Time to think, to read, to investigate the natural world without the pressures of commerce or the distractions of court life. And this is precisely how John Michell, an English parson with a remarkable mind, spent his days. By the 1,780 seconds, Michell had absorbed the revolutionary work of Isaac Newton. A century earlier, Newton had unveiled his theory of universal gravitation, a breakthrough that had sent shockwaves through the scientific community. Gravity, Newton demonstrated, wasn't some mysterious force that only affected objects near Earth. It was universal, literally. Anything with mass, anywhere in the universe, exerted a gravitational pull on everything else. The force was instantaneous, reaching across any distance without delay. Nothing could escape gravity's influence. Not planets, not stars, not even. And this is where Michell's mind began to wander into uncharted territory, light itself. Now, Newton had also proposed that light consists of tiny particles, minuscule corpuscles streaming from luminous objects. We now call these particles photons, but the essential idea was the same. If light is made of particles, and if gravity acts on all matter universally, then gravity should affect light. The particles of light, however small, however fast, should feel the pull of massive objects. Michell also knew something else crucial. Light travels fast, but not infinitely fast. Earlier in the century, the astronomer James Bradley had managed to measure the speed of light through careful observations of distant stars. As Earth orbits the Sun, our planet's motion combines with the incoming light from stars to create a subtle effect called aberration. Stars appear to shift slightly in position depending on Earth's velocity through space. By measuring these tiny shifts with exquisite precision, Bradley calculated that light travels at roughly 180,000 miles per second. Extraordinarily fast, yes, but not infinite. And that distinction would prove critical. Michell understood something else that seems intuitive to us now, but required careful thought in his era. When you throw an object upward, it falls back down. Throw it harder, and it goes higher before falling. Throw it hard enough, really, impossibly hard, and it won't fall back at all. It will escape Earth's gravity entirely and reach space. This critical speed is called the escape velocity. It's the minimum launch speed needed to break free from a planet's gravitational grip and reach infinity. For Earth's moon, with its relatively weak gravity, the escape velocity is about 2.4 kilometers per second. For Earth itself, it's higher, roughly 11.2 kilometers per second. For massive Jupiter, nearly 60 kilometers per second. And for our Sun, with its enormous mass, escape velocity climbs to about 617 kilometers per second. Now Michell made his logical leap, the one that would echo across centuries. Newton's equations made it straightforward to calculate escape velocity for any object based on its mass and size. The more massive the object, and the more compressed that mass, the higher the escape velocity. So Michell asked himself a simple question. What if you had an object so massive and so dense that its escape velocity exceeded the speed of light? Think about what that would mean. Light emitted from such an object's surface would try to escape, streaming outward as light always does. But the gravitational pull would be so intense that even photons, traveling at their maximum possible speed, couldn't overcome it. They would be pulled back, trapped by gravity. The object would be invisible, gravitationally massive, powerfully influential on everything around it, but completely dark. It would be a void in space, a region that devours light rather than emitting it. Michell had just described, in 18th century Newtonian terms, what we now call a black hole. The language he used belongs to an older physics, one that Einstein would later revolutionize. But the core concept is unmistakable. Michell's dark star is clearly recognizable as a black hole, even though that term wouldn't be coined for almost 2 more centuries. The idea was brilliant. It was also utterly useless, at least in practical terms. No one, in the 1,780 seconds, had any reason to believe such objects actually existed in nature. There was no way to detect them, no observations that demanded their existence as an explanation. So Michell's work was filed away, relegated to the scientific equivalent of a curiosity cabinet, where it gathered dust for over a century and a half. The next chapter in this story would unfold in a far darker place, the blood-soaked trenches of World War I. Karl Schwarzschild was a German astronomer of exceptional talent. When war broke out in 1914, he volunteered for military service, despite being in his 40s, an age when he could have avoided the front lines. But duty called, and Schwarzschild found himself in the nightmare landscape of trench warfare, surrounded by death and devastation. Seeking escape from the horror, Schwarzschild turned to what he loved, mathematics and physics. And in particular, he became fascinated with Albert Einstein's brand new theory of general relativity. Einstein had published his special theory of relativity in 1905, revolutionizing our understanding of space, time, and motion. But that theory didn't include gravity. For 10 years, Einstein struggled to extend his framework to encompass gravitational phenomena. Finally, in late 1915, he succeeded, presenting his general theory of relativity to the world. The theory was breathtaking in its elegance and horrifying in its complexity. It required 10 interrelated equations to describe how mass and energy curve space-time, and how that curvature in turn dictates how objects move. When Einstein first wrote down these equations, they looked nearly impossible to solve. No one knew where to even begin. Schwarzschild, sitting in his trench with death all around him, decided to try. He looked for the simplest possible scenario he could imagine: a perfectly spherical mass, concentrated at a point with space-time arranged symmetrically around it. Plugging this setup into Einstein's equations, working through the mathematics with painstaking care, Schwarzschild found a solution. It was the first exact solution to Einstein's equations ever discovered. Today, we call it the Schwarzschild solution, and it remains one of the most important results in all of gravitational physics. The solution described how space-time behaves around a spherical mass. Near the mass, space-time curves dramatically. Far away, the curvature fades, and space-time becomes nearly flat. This much was expected. But Schwarzschild's solution contained something unexpected, something deeply strange. As you move inward from infinity toward the central mass, there exists a critical distance where the mathematics does something peculiar. Certain terms in the equations approach zero, others approach infinity. The solution appears to break down completely. What did this mean? Was it just a mathematical artifact, a quirk of the equations with no physical significance? Or did it represent something real, something profound about the nature of gravity and space-time? It took decades to fully understand what Schwarzschild had found. Those infinities and zeros at the critical radius now called the Schwarzschild radius indicated the presence of an event horizon, a spherical boundary surrounding the central mass that represents a point of no return. Here's how it works. Nothing can travel faster than light. That's a fundamental law of physics, carved into the very structure of space-time. Outside the Schwarzschild radius, light can escape to infinity. A photon emitted outward from just beyond this boundary will gradually overcome the gravitational pull and reach distant space. But inside the Schwarzschild radius, escape becomes impossible. Even light, traveling at maximum speed directly away from the center, cannot overcome gravity's pull. The horizon is a one-way membrane. Cross it, and your fate is sealed. There is no escape, no reprieve, no clever trick or advanced technology that can save you. The laws of physics themselves forbid it. Anything crossing the event horizon enters a region where all paths lead inexorably inward. Time itself points toward the center. An astronaut who crosses the horizon would find themselves falling, always falling, with the gravitational pull growing stronger every moment. Eventually, they would reach the singularity, a point where space-time curvature becomes infinite, where the classical laws of general relativity break down completely, where our understanding of physics simply ends. This was eerily similar to Michell's calculation from over a century earlier. Both men had found, using different physics, that there exists a critical radius where escape velocity equals the speed of light. Compress enough mass into a small enough space smaller than the Schwarzschild radius for that mass, and gravitational collapse becomes inevitable. For our Sun, the Schwarzschild radius is about 3 kilometers. Compress the entire Sun into a sphere smaller than a modest city, and it would collapse into a black hole. For Earth, the critical radius is less than a centimeter, about the size of a marble. A human body's Schwarzschild radius is unimaginably small, on the order of 10 to the minus 23 meters, smaller than an atomic nucleus. And if you could somehow gather all the stars, gas, and dust in the Milky Way galaxy and compress them into a radius smaller than about 0.2 light-years, you'd create a truly colossal black hole, a monster that would dwarf anything in our actual universe. Schwarzschild discovered his solution in 1915, while shells exploded around him and soldiers died by the thousands in the muddy hell of the Western Front. He sent his results to Einstein, who was astonished. Here was the first crack in what seemed like an impenetrable mathematical fortress. Sadly, Schwarzschild wouldn't live to see the full implications of his discovery. He contracted a painful autoimmune disease at the front and died in 1916 at age 42. His solution, like Michel's work before it, seemed like an abstract curiosity. Interesting mathematics, perhaps, but surely not relevant to the actual universe. For the next 50 years, black holes remained in the scientific backwater. Physics was revolutionized by quantum mechanics in the 1,920 seconds, 30 seconds, and 40 seconds. Atom bombs were built. Particle accelerators probed the fundamental constituents of matter. Meanwhile, general relativity and gravitational physics were largely ignored, considered a stagnant field with few interesting questions and fewer interesting answers. The physicist Richard Feynman, never one to mince words, attended a conference on gravity in the early 1,960 seconds. His assessment was brutal. "I am not getting anything out of the meeting. I am learning nothing. Because there are no experiments, this field is not an active one. So few of the best men are doing work in it. The result is that there are hosts of dopes here, and it is not good for my blood pressure." But Feynman's dismissal would soon prove spectacularly wrong. In the late 1,960 seconds, everything changed. A combination of theoretical breakthroughs and stunning astronomical observations brought black holes roaring back to the forefront of physics, where they've remained ever since. And in the public imagination, one name became synonymous with this renaissance more than any other: Stephen Hawking. Born in 1,942 inches, Oxford, England, Stephen Hawking seemed destined for a comfortable career in science. He studied physics as an undergraduate at Oxford, performing well but without exceptional effort. He then moved to Cambridge to pursue a PhD in theoretical physics, a standard path for a bright young scientist. But during his doctoral work, Hawking's life transformed in two profound and connected ways. First, at age 21, he was diagnosed with amyotrophic lateral sclerosis, known as ALS or motor neuron disease. This degenerative condition destroys the nerve cells that control voluntary muscle movement. Patients gradually lose the ability to walk, speak, swallow, and eventually breathe. The typical prognosis from diagnosis was about 18 months. Facing the prospect of imminent death, Hawking experienced a second transformation. He began to work. Really work. For the first time in his academic career, he threw himself into physics with fierce intensity and focus. If his time was limited, he would make it count. He would leave a legacy. Against all odds, Hawking didn't die in 18 months. He outlived his prognosis by more than 50 years, eventually passing away in 2018 at age 76, by which time he had become one of the most famous scientists in the world. The scientific achievements that earned him that fame came primarily from a period of extraordinary creativity between 1,967 and 1,974, during which Hawking collaborated closely with the mathematician Roger Penrose. Together, they revolutionized our understanding of black holes and general relativity. One of their key contributions was a set of theorems about gravitational collapse. Imagine starting with a cloud of heavy particles, all pulling on each other through gravity. What happens? Intuitively, it's not obvious. Maybe they collapse into a dense object. Maybe they scatter, some slingshotting away through gravitational interactions. The outcome seems uncertain, dependent on precise initial conditions. Hawking and Penrose proved that under quite general conditions that apply to realistic astrophysical scenarios, gravitational collapse is inevitable. And the endpoint of that collapse is equally inevitable: a singularity in spacetime, surrounded by an event horizon, a black hole. This wasn't speculation or conjecture. It was a mathematical proof. Under the right circumstances, black holes must form. There's no escape clause, no alternative possibility. Hawking and Penrose also introduced new ways of thinking about the structure of spacetime near black holes. Penrose developed elegant diagrams that compress the infinite complexity of space-time geometry into simple, comprehensible pictures. In these diagrams, light always travels at 45-degree angles, making it easy to see which regions of space-time can affect which other regions, what physicists call causal structure. The event horizon appears in these diagrams as the boundary beyond which no causal influence can reach the outside universe. It's a perfect visualization of the point of no return. As Hawking's body gradually failed, his mind soared to ever greater heights. And at the same time, telescope technology was advancing rapidly. For the first time, satellites could carry telescopes above Earth's atmosphere, allowing observations not just in optical light but across the entire electromagnetic spectrum. X-ray telescopes revealed a sky far busier and stranger than anyone had imagined. One source in particular caught astronomers' attention: Cygnus X1, an extraordinarily bright and compact X-ray source. The energy output was enormous, concentrated in a tiny region of space. What could produce such intense X-ray emission from such a small volume? The only viable explanation was a black hole, with the X-rays generated by matter being violently accelerated as it spiraled inward toward the event horizon, heating to millions of degrees in the process. Cygnus X1 was the first confirmed black hole candidate. Since then, astronomers have identified potentially hundreds of millions of black holes in our galaxy alone. In 2015, the LIGO Observatory directly detected gravitational waves from colliding black holes, ripples in spacetime itself, confirming Einstein's predictions and opening a new window on the universe. But the excitement about black holes wasn't confined to observatories and telescopes. On blackboards and in late-night calculation sessions, theoretical physicists explored black holes as mathematical objects, pushing the equations to their limits, uncovering properties that seem to defy common sense. Consider the human face again. Faces are familiar, easily recognizable, yet incredibly complex. How many numbers would you need to completely specify a face? Countless measurements. The exact contour of every feature, the distribution of every pore and freckle, the subtle variations in skin tone and texture. The information required is enormous. Black holes, by contrast, objects that seem far more exotic and mysterious, are shockingly simple. This simplicity was reflected in the solutions to Einstein's equations. After Schwarzschild's original discovery in 1915, physicists found a few generalizations. In 1916, the Reissner-Nordström solution described an electrically charged black hole. But then progress stalled for decades. It wasn't until 1963 that the next major breakthrough arrived: the Kerr solution, discovered by New Zealand mathematician Roy Kerr. The Kerr solution describes a rotating black hole with angular momentum, spinning on its axis like a cosmic top. Imagine a massive ballerina, arms outstretched, spinning rapidly. She's heavy enough to be almost, but not quite at the threshold density for black hole formation. As she pulls her arms inward, her rotation speeds up dramatically, as dictated by conservation of angular momentum. And at a certain point, she crosses the density threshold. Collapse is instantaneous, but the angular momentum doesn't disappear. It can't disappear. Angular momentum is conserved. Instead, it gets encoded into the structure of the black hole itself. The Kerr solution describes exactly this: a black hole carrying the rotational momentum of whatever collapsed to form it. But why were there so few black hole solutions? Only Schwarzschild, Kerr, and their charged variants, the Reissner-Nordström and Kerr-Newman solutions. Physicists searched for other possibilities, trying to construct black holes with additional properties, extra parameters, more complexity. They found nothing. And gradually, they realized this wasn't due to lack of effort or mathematical ingenuity. It was a fundamental feature of black holes themselves. In the early 1970 seconds, physicists proved what's now known as the black hole uniqueness theorem, a result with staggering implications. Most astronomical objects possess nearly infinite distinguishing characteristics. Consider a quasar, a supermassive black hole actively consuming matter at a galactic center, surrounded by an accretion disk so hot and violent it outshines entire galaxies. The detailed structure of a quasar involves trillions upon trillions of parameters: the distribution of matter in the disk, the precise configuration of magnetic fields, the spectrum of radiation at every wavelength. the turbulent flow patterns in the infalling gas. Stars, though simpler than quasars, still come in staggering variety. From the most massive stars that burn bright and die young in spectacular supernovae, to tiny red dwarfs that will smolder for trillions of years, each star is unique. Even their surfaces show complexity. Sunspots, flares, convection cells, prominences, each feature requiring numerous parameters to describe. Even a simple asteroid has individuality craters marking its history, variations in composition across its surface, in irregular shape, determined by countless ancient collisions. But black holes? Black holes are different. The uniqueness theorem proved that black holes are completely characterized by exactly three properties: mass, electric charge, and angular momentum. That's it. Nothing else matters. No other parameters exist. Three numbers capture everything about a black hole. The physicist John Wheeler, who had a gift for memorable phrases, summarized this with characteristic elegance. Black holes have no hair. By this he meant that black holes have no distinguishing features beyond those three numbers. No hair or individual characteristics to tell them apart. Wheeler also popularized the term black hole itself, which replaced earlier awkward phrases like frozen star or collapsed object. Every black hole anywhere in the universe, regardless of how it formed or what fell into it, can be completely classified by its mass, charge, and spin. Behind the event horizon, an almost infinite variety of formation scenarios, collapsing stars, merging black holes, accreting gas clouds, all reduced to the same three numbers. This is where the mystery deepens. How can vastly different formation processes, involving radically different initial conditions and evolutionary paths, all produce objects characterized by just three parameters? Where does all the other information go? When physicists encounter this question, when they hear about many different microscopic configurations giving rise to a few macroscopic parameters, they immediately recognize it. This is the language of thermodynamics, the science of heat, temperature, and entropy. Look around the room you're in right now. It's filled with air gas at a certain temperature and pressure. You can feel these properties. A blast of hot air feels different from cold air. Your ears pop when cabin pressure changes during a flight. But you can't feel individual air molecules. They're too small, too numerous, moving too fast. Any given room contains an incomprehensibly large number of molecules, something like 10 to the 26 particles, all bouncing off each other in constant chaotic motion. When we say a room is hot, we're not tracking every individual molecule. We're making a statement about the average behavior of countless particles. Heat is actually molecular kinetic energy. Faster moving molecules correspond to higher temperature, but we don't experience it that way. We just feel hot or cold. This is the essence of thermodynamics, describing systems with many internal configurations, using a few bulk parameters. Gases have temperature and pressure. Black holes have mass, spin, and charge. In both cases, a few numbers characterize systems that possess enormous internal complexity. And there's a specific quantity that measures this hidden complexity: entropy. Entropy counts the number of internal microconfigurations consistent with the macroscopic parameters you can measure. For a gas at a given temperature and pressure, entropy measures how many different arrangements of individual molecules could produce those bulk properties. The more possible arrangements, the higher the entropy. For a gas, this makes intuitive sense once you know gases consist of many tiny molecules bouncing around. Higher temperature means molecules moving faster on average. And there are simply more ways for molecules to move fast than to move slowly. At the absolute slowest zero velocity, there's only one configuration: every molecule stationary. But at higher speeds, molecules can move in countless different directions and speeds while maintaining the same average kinetic energy. More possibilities means higher entropy. This entropy concept, familiar from everyday thermodynamics, increases with temperature for gases. Hot objects have higher entropy than cold ones of the same size. This seems obvious once you understand the microscopic picture. But can these thermodynamic concepts really apply to black holes? One of the strangest, most mysterious objects in all of physics, an object with no swirling atoms, no jiggling molecules, nothing but warped space-time and an event horizon? Remarkably, astoundingly, the answer is yes. Black holes are thermodynamic objects. They have entropy. They have temperature. The concepts apply just as rigorously as they do to gases in rooms or water in kettles. This revolutionary insight emerged in the early 1970 seconds, first suggested by a graduate student named Jakob Bekenstein, and later fully developed by Stephen Hawking himself. Bekenstein was studying under John Wheeler at Princeton. During their discussions, Wheeler posed an interesting puzzle. Imagine mixing hot tea with cold tea. The entropy of the combined mixture increases. That's basic thermodynamics. The second law demands it. But now suppose you throw the mixed tea into a black hole. Everything gets swallowed up. The tea, along with all information about its temperature and entropy, vanishes behind the event horizon. The black hole's external appearance changes only slightly. Its mass increases by the mass of the tea. So where did the entropy go? Did it simply disappear? This seemed impossible. The second law of thermodynamics, which states that the total entropy of the universe must always increase or stay constant, never decrease, is one of the most fundamental principles in physics. The 20th century astrophysicist Arthur Eddington once said, "The law that entropy always increases holds, I think, the supreme position among the laws of nature." If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Bekenstein reasoned that if the second law is truly universal, then throwing tea into a black hole shouldn't decrease the universe's total entropy. Instead, the black hole itself must have entropy. When the tea falls in, the tea's entropy doesn't vanish, it gets added to the black hole's entropy. This led Bekenstein to a remarkable conclusion. Black holes must possess entropy, what we now call Bekenstein-Hawking entropy. It was a truly bizarre discovery. But what did it mean? What were these internal configurations being counted by black hole entropy? Let's pause to consider which black holes are the hottest in the universe. Since the 1960 seconds, astronomers have discovered a vast population of black holes with enormously varying masses. The heaviest known examples, monsters like TON 618 or Phoenix A, weigh around 100 billion times the mass of our Sunday 618. These ultramassive black holes lurk at the centers of distant galaxies, powering brilliant quasar jets that can outshine their entire host galaxies. At the other extreme, the lightest confirmed black holes are stellar mass objects, corpses of massive stars weighing just a few solar masses. Candidates for the lightest known black holes include companions to pulsars like PSRJ 500 and 14402e, or orbital partners to stars like the red giant V723 Monday. Here's the stunning part. These miniature black holes are billions of times hotter than the supermassive giants that power entire galaxies. Not that any black hole is hot by everyday standards. Even the hottest stellar mass black holes have temperatures of only about 100 millionth of a degree above absolute zero. The supermassive ones are incomprehensibly colder still. But the relationship is clear. Big black holes are cold. Small black holes are relatively hot. Where does this temperature come from? How can a black hole, an object defined by the fact that nothing escapes it, have a temperature at all? By the early 1970 seconds, Bekenstein and Hawking had established that black holes should have entropy. The second law of thermodynamics could be preserved. Throw matter into a black hole, and the black hole's entropy increases appropriately. The universe's total entropy marches forward. But as Hawking thought more deeply about this picture, he identified a problem. Imagine hot gas falling into a black hole and being completely absorbed. The resulting black hole should be cold and dark. Nothing comes out. It's a perfect absorber. In ordinary thermodynamics, when hot and cold objects interact, the cold object warms up. Mix hot and cold water, and you get warm water. The temperatures equilibrate. But black holes seem to violate this. They absorbed hot matter and remained at absolute zero temperature. They gave nothing back. This bothered Hawking. If black holes truly have entropy, and entropy relates to temperature through classical thermodynamic relations, then black holes should have non-zero temperature. They should radiate, just like any other hot object. But black holes are black precisely because nothing escapes them, not even light. How could they radiate? This is where Hawking made his most famous contribution to physics. He proposed and then proved through detailed calculation that black holes do have temperature, not a mathematical temperature, not an analogous quantity, but actual physical temperature, with exactly the same meaning as the temperature of your coffee or your oven or the summer air. Black holes are hot. The most exotic objects in the universe behave, thermodynamically, just like ordinary matter. The classical laws of thermodynamics relate entropy to temperature through a precise formula. Temperature equals the inverse of the rate of change of entropy with energy. For a gas, adding energy increases the number of possible molecular configurations, and we can calculate the resulting temperature. For black holes, Bekenstein and Hawking had shown that entropy is proportional to the area of the event horizon. For a simple Schwarzschild black hole, this entropy grows as the square of the mass energy. Applying the classical thermodynamic formula to this relationship yields a striking result. Black holes must have temperature, and this temperature is inversely proportional to the black hole's mass. Big black holes are cold. Small black holes are hot. A typical stellar mass black hole in our galaxy, perhaps 10 times the Sun's mass, has a temperature around 1/1000th of a degree Kelvin. Utterly frigid, far colder than the cosmic microwave background radiation filling empty space. But a much smaller hypothetical black hole, say one with the mass of Mount Everest, compressed to a point would have a temperature of hundreds of billions of degrees, far hotter than the cores of the most massive stars. This inverse relationship leads to bizarre consequences. Normal fires start hot and gradually cool as they radiate heat away, eventually dying down to glowing embers and then nothing. Black holes behave oppositely. As they radiate and lose mass, they get hotter, not cooler. The radiation accelerates. Eventually, a black hole evaporates completely in a final, brilliant flash of radiation. Strange, counterintuitive, but characteristic of these bizarre objects. But why do black holes have temperature at all? If nothing escapes from beyond the event horizon, how can they radiate? The answer lies in quantum mechanics, specifically in Heisenberg's uncertainty principle. Imagine yourself hovering just outside a black hole's event horizon. You've got a rocket with enormously powerful engines, firing constantly to keep you from falling in. You're balanced right at the edge, close enough to the event horizon that one small mistake would seal your fate. Place 2 beacons on your rocket, one pointing toward the black hole, one pointing away. Light from the inward-pointing beacon immediately crosses the horizon and falls inevitably toward the singularity, lost forever. Light from the outward-pointing beacon escapes successfully, traveling off to distant space. This setup captures something essential about the event horizon. It's a sharp boundary between 2 radically different fates. Now we need to invoke a strange feature of quantum mechanics: vacuum energy and virtual particles. In quantum mechanics, even the coldest, emptiest vacuum isn't truly empty. The uncertainty principle forbids perfect stillness. Instead, the vacuum seethes with quantum fluctuations, brief violations of energy conservation where particle-antiparticle pairs spontaneously appear and then annihilate, returning their borrowed energy to the vacuum. These are called virtual particles. They exist for tiny fractions of a second, then vanish. The more energy borrowed, the shorter the allowed time. Provided the books balance quickly enough, energy borrowed and energy returned, no laws of physics are violated. This happens everywhere, constantly, throughout all of space. It's a fundamental feature of quantum field theory, well established and experimentally verified through effects like the Casimir force. Now, consider what happens near a black hole's event horizon. The vacuum still produces these fleeting particle-antiparticle pairs. But the horizon introduces a directionality, an inward pull. Imagine a pair of photons created just outside the horizon through a quantum fluctuation. Normally, they'd exist briefly and then recombine, returning their borrowed energy harmlessly. But near the horizon, one photon might cross it during that brief existence, falling into the black hole, while its partner escapes to infinity. The pair can no longer recombine. They're permanently separated. The escaping photon carries away energy. But where did that energy come from? It was borrowed from the vacuum, and now it can't be returned. Instead, the black hole must pay the debt. The black hole's mass energy decreases very slightly. The net result: one photon escapes to infinity, carrying energy away from the black hole. The black hole loses mass. Detailed calculations confirm Hawking's insight. The spectrum of escaping radiation is exactly thermal, precisely what you'd expect from a hot object with temperature given by Hawking's formula. Black holes aren't black after all. They glow, albeit extremely faintly. This is Hawking radiation, one of the most profound results in theoretical physics, sitting precisely at the intersection of quantum mechanics, thermodynamics, and general relativity. But this discovery, remarkable as it was, immediately created another problem. If black holes radiate, they lose mass. Over immense spans of time far longer than the current age of the universe for stellar mass black holes, they would evaporate completely. Now imagine forming a black hole by throwing in countless encyclopedias, databases, libraries, every piece of information ever recorded by every civilization in cosmic history. All of it falls past the event horizon and vanishes from view. The black hole sits there for eons, slowly radiating Hawking radiation. Eventually, it evaporates completely, leaving only a cloud of thermal radiation. So, what happened to all that information? According to Hawking's calculation, the emitted radiation has a perfectly smooth thermal spectrum, featureless, containing no trace of what originally fell in. The information seems to have been destroyed, erased from existence. But this contradicts a fundamental principle of quantum mechanics. Information is never destroyed. In quantum systems, information about initial states is preserved as the system evolves. You can scramble it, encode it in complicated ways, but never truly erase it. This is the black hole information paradox, and it plagued physicists for decades. Some argued that black holes represent a true exception, that combining gravity and quantum mechanics creates a situation where information can genuinely be destroyed. Others insisted the information must survive somehow, encoded in ways we don't yet understand. The debate raged through the 1,980 seconds and 1,990 seconds. Hawking himself initially believed information was destroyed. Others, including many prominent physicists, disagreed vehemently. The resolution would come from an unexpected direction. The holographic principle, one of the strangest and most profound ideas in modern physics. The first hint came from examining Bekenstein and Hawking's entropy formula more carefully. There's something odd about it that's easy to miss. Black hole entropy is proportional to the horizon's area, not the black hole's volume. This is unusual. For ordinary systems like gases, entropy grows with volume. Double the size of a container holding gas at fixed pressure, and you double the number of possible molecular configurations. Entropy scales with volume three-dimensional space. But black holes are different. Their entropy scales with the two-dimensional area of the event horizon. Think about what entropy means. It counts internal configurations. For a gas, we can imagine dividing space into tiny cells, each either occupied or empty by a gas molecule. Each cell can be on or off. With n cells, there are n possible configurations. The number grows exponentially with the number of cells, which scales with volume. For black holes, the Bekenstein-Hawking formula suggests something different. The counting should be done on the horizon, a two-dimensional surface, not in the three-dimensional interior. It's as if all the information about the black hole's interior is somehow encoded on the horizon's surface, like a hologram encoding three-dimensional information in a two-dimensional pattern. This led to the holographic principle, developed through the 1,990 seconds by theorists including Gerard Hooft and Leonard Susskind. The physics in a region of space can be completely described by information encoded on the boundary of that region. Gravitational systems in three spatial dimensions are equivalent to non-gravitational quantum theories living on the two-dimensional boundary. The interior dimension is, in some sense, redundant. It can be reconstructed from boundary data. This idea, now formalized as the ADS, CFT correspondence, is supported by thousands of calculations and has become one of the pillars of modern theoretical physics. It suggests that a gravitational theory in, say, 5 dimensions and a non-gravitational quantum theory in 4 dimensions are actually the same theory, just expressed in different mathematical languages. The holographic principle offered a resolution to the information paradox. In the gravitational description, we worry about information falling into the black hole and potentially being lost at the singularity. But in the alternative holographic description, the non-gravitational quantum theory on the boundary, there's no singularity, no horizon, no mystery. It's just an ordinary quantum system evolving in an ordinary way. In ordinary quantum mechanics, information is always preserved. It might get scrambled beyond practical recognition, but it's there. So in the holographic picture, the information is never lost. It's encoded on the horizon and eventually carried away in subtle correlations in the Hawking radiation. The radiation looks thermal random and featureless only if you examine it crudely. Look closely enough at the correlations between emitted particles, and the information is there, encoded in quantum entanglement patterns. This is now the prevailing view among most physicists. The information survives, encoded in the radiation. Black holes don't violate quantum mechanics after all. But this raises yet another question. What are black holes actually made of? What are these internal configurations that the entropy counts? For a gas, we know the answer: molecules at different positions and velocities. What's the analogous answer for black holes? This question seems impossible to answer experimentally. To probe the interior of a black hole, you'd need to cross the event horizon. But once you cross, you can never return to report your findings. The interior is causally disconnected from the outside universe. Experiments can't reach there, but mathematics can. Physicists can study simplified mathematical models, toy universes that don't exactly match ours but share key features. By understanding these tractable models, they hope to gain insights into real black holes. In 1995, Andrew Strominger and Kumran Vafa, working at Harvard, studied a specific type of black hole in string theory. These weren't realistic astrophysical black holes. They lived in a mathematical universe with 5 spatial dimensions and possessed special symmetries not present in nature. But they were black holes nonetheless, and they satisfied the Bekenstein-Hawking entropy formula. Strominger and Vafa managed to count precisely and explicitly the microscopic states that could form these black holes. In string theory, the answer involved extended objects called branes. By counting all possible configurations of branes, they derived the entropy. And remarkably, their count exactly matched the Bekenstein-Hawking formula. It was a triumph. For this special class of black holes, physicists could peer behind the veil and see what the entropy was counting. Unfortunately, these special black holes don't exist in our universe. They require extra dimensions and symmetries we don't observe. For real astrophysical black holes, monsters like Cygnus X1 or TON 618, we still don't know what the internal microstates are. We can't yet describe precisely what a real black hole is made of at the microscopic level. But the holographic principle gives us hope. It suggests the answer doesn't lie in the interior at all, but rather in the structure of the horizon itself, in the quantum geometry of that two-dimensional surface enclosing the void. Perhaps one day we'll understand it completely. Perhaps we'll find a full theory of quantum gravity that describes black hole microstates as clearly as we describe gas molecules. Or perhaps black holes will continue to guard their secrets, revealing them only gradually across centuries of effort. Nearly 300 years after John Michell first imagined dark stars, and over a century after Carl Schwarzschild solved Einstein's equations in a wartime trench, black holes remain the universe's deepest mystery. They challenge our understanding of space, time, information, and reality itself. They sit at the intersection of our two greatest physics, theories, general relativity, and quantum mechanics, and they seem to demand something beyond both, some deeper theory we haven't yet discovered. 3 numbers define them completely. Yet those 3 numbers hide infinite complexity, infinite possibility, infinite mystery. What is inside a black hole? After all our progress, after all our insights, the honest answer is still, we don't know. But we're getting closer. With each new gravitational wave detection, each new theoretical breakthrough, each new mathematical technique, we peel back another layer of the mystery, and perhaps that's fitting. Perhaps the universe's strangest objects should be the last to yield. Their secrets should resist our understanding the longest, demanding our deepest thinking, our most creative mathematics, our most profound insights about the nature of reality. Black holes have no hair, but they have infinite depth. And that depth calls to us still, across the void, inviting us to look deeper, think harder, imagine further. The journey is far from over. The most exciting discoveries may still lie ahead.